Hey everyone, I'm Matt.
I'm Paul.
As Diane said, we're from Uber. We're SREs on the observability team where we work on Uber's open source metric platform. And today we're going to share with you some of our experience building an operator for part of it. So we work on M3DB, which is Uber's open source time series database. It's part of M3, which is Uber's open source metric stack. So M3DB is the core distributed time series database that sits at the center of M3. We also have other components like our fault-tolerant aggregation tier, our distributed query engine, all of which act as kind of a way to use M3DB as just a general time series database or as a long-term store for Prometheus. When we first built M3DB, to give you a sense of M3DB's usage at Uber, we have a little over 1,100 instances running M3DB. They all do, in post-aggregation, 33 million writes per second, which comes out to about 55 gigabits per second. And we store a little over 9 billion unique metric IDs. When we first built M3DB in 2016, operating it was pretty simple. We pretty much ran M3DB in 2 data centers, and we had 1 cluster per data center. The clusters also shared a static configuration. Our only use case back then was like real-time alerting and dashboard introspection. So we just stored metrics at 10 seconds for a 10-second resolution for 2 days. But when you fast forward to 2019, things aren't nearly as simple. So we run M3DB in more data centers. There are more clusters per data center. The clusters are larger, and they no longer share a static configuration. So we have some clusters that store high-resolution metrics at like 1 second for 6 hours, and then some clusters that store low-resolution metrics at, say, an hour for up to 5 years. On top of all this configuration complexity, we also run M3DB in multiple cloud providers where Uber has a presence. So when you put this all together, clusters grew like by 20 times. Engineers stayed relatively the same. And while M3DB itself is pretty easy to manage on like a cluster level, we really needed something that would kind of help automate this whole cluster lifecycle. And Paul's going to talk a bit about what that looks like.
Thanks, Matt. So with all these clusters now in multiple regions, we have to kind of discuss how did we even manage it. So we kind of broke that down into 2 life cycles that might be familiar to everybody here. Here's our reactive lifecycle. We have a problematic node that happens. Engineer gets paged by PagerDuty, wakes up, SSH is in there, and then basically tries to reboot the host or add capacity or remove capacity to remediate the issue. And then everything's back at a steady state and healthy. And this happens throughout an entire week for their on-call shift. At the end of that week, we assemble the engineering team, we review all the problems that arose through these various clusters, and kind of come up with an action plan of, do we need to do some capacity management, or how do we handle the management of these hosts? And it takes a little bit of time away from everybody's schedule at the end of the week. And then after all is said and done, there's an action plan that's formulated, and an engineer has to go out and actually enact that plan. And it could take a lot of time away from that engineer to actually do core feature development or whatnot for the actual thing. So let's talk about why we went the operator route, because we wanted to make this experience a lot more smoother for our engineers. So first, before we even went down thinking about how to automate this, we had to understand the problem space that we were in. So let's talk about some of the features of M3DB at its core to kind of understand what we had to automate. First and foremost, M3DB is a sharded distributed time series database. So the first thing that we have here is basically each piece of data upon ingestion into M3 is basically sharded into a respective partition for separate the failure domains that we have inside there. Each of these shards are actually replicated furthermore to separate out even further failure domains that are within the database itself. And so all shards are replicated by a factor of 3 by normal settings, I would say. And it's always replicated and synced in real time at all times. So with those given primitives, let's talk about some of the features that we settled on with here.
So a lot of the things that we were thinking about when we were talking about our requirements of what we need out of a platform Given that we're working on database, really one of the main ones that stood out was storage. We needed, whatever system we chose had to have features to support a demanding stateful workload. So M3DB requires access to low latency storage, and we require access to the storage across all of our clusters. We have internal workloads at Uber that randomly query large time series, ranging from hours to years for things like alerting or SLA tracking, capacity planning, and our stakeholders expect to have access to all of this data in a real-time manner. To give you a sense of what we mean by like performant stateful primitives, let's take a look at some of the ways you might store state in a containerized application. So one option would just be to not store your state at all. An M3DB instance's data would live as long as its container. This might be nice as you would have direct access to the host disk and all the speed that comes with that, but otherwise it would be pretty terrible. So for one, there's no durability of the data. And this means that as containers are upgraded or restarted, even if that's in place, they would have to restream all of the data that they're responsible for from their peers, which could be terabytes of data. And then in addition to that being inefficient, it also has dangerous reliability implications. So when an M3DB instance is coming up, or as we call bootstrapping, it's available, it takes writes, but it's not available for reads, meaning that while an instance is streaming data from its peers, you're at a reduced read replication factor. So another option for storing your state in a more durable manner might be to use remote storage. So this is pretty popular on your neighborhood cloud provider. You can use something like a block store. So in this case, we still weren't really super happy with this as there is increased latency. Additionally, it seemed pretty inefficient for us to pay someone to replicate data at the block layer that we're already replicating at the application layer, and then to do that slower with potentially varying performance characteristics. But honestly, the main thing was that this was less portable for us across cloud providers and our data centers. So even different cloud providers, their remote storage, their block store solutions kind of have different performance characteristics. And then also, we just weren't really comfortable using network storage inside of our data centers. So another option for remote storage that we've seen some systems take is to use a remote object store. So in this case, you would say deduplicate all of your data, and then you would just store one copy of it on like your cloud provider's object store. So this is kind of nice since you're only paying to store one copy of the data, but there's even worse latency introduced. And then this still brings back the problem that as containers are moved around, they would potentially have to pull all of this data that they're responsible for back down from the object store. So this left us searching.
Yeah, so you can see the metrics we have right here, durability, performance, and efficiency, and the previous flaws of the other approaches that Matt mentioned really didn't meet all the checkboxes that we were looking for. So we went out and did some evaluation, and we settled on Kubernetes because they actually checked all these boxes for us eventually. And one of the first features was the local persistent volumes that they provide. And so this type of abstraction was very portable for us to do on-prem as well as inside the cloud to meet our needs. In addition to that, local volume gives us that speed that we were looking for to provide that low latency throughput that our customers would expect from that. And so we settled on the local volumes of Kubernetes to check all these boxes for us.
Additionally, some more Kubernetes features that were really helpful for us was the combination of node affinity and stateful sets. So with stateful sets, we got things like strict ordering of pod operations, whether that just be a maintenance rolling restart or a cluster version upgrade. And then combining that with node affinity, we were able to kind of express our requirements for failure domains. So to give you an example of what we mean by that, in our internal data centers, we use Uber's provisioning tooling to make sure that the physical hosts that M3DB runs on are provisioned and scheduled across racks and other failure domains in the data center. Once those instances are up, M3DB itself, the placement algorithms take care of distributing the shards across those failure domains such that no loss of a single failure domain can cause the cluster to lose quorum. So using node affinity, we are able to express this really nicely in our cloud environment. So what we could pretty much do is pin stateful sets of M3DB to zones in the cloud, and then make sure, and then we would be guaranteed that we would get all these pods evenly distributed across all these failure domains. And then again, when the M3DB instances come up, they actually just distribute the shards across all the zones.
So let's talk about some of the findings that reoccurred while we were doing the development of the operator itself. First and foremost, development and CI are going to be on the forefront of your mindset when you're doing that. And first, we found out with the blistering pace of the Kubernetes release cycle every quarter, there were a lot of breaking changes. So one of the first things we discovered was to have a proper end-to-end test that would basically install the operator, do some rudimentary checks, and make sure it's happy. Everybody loves unit tests, but when you actually see the actual end-to-end lifecycle work, it makes you much more confident in there. Helped us catch a lot of bugs with breaking changes that came from the API changes from Kubernetes. Another thing that we ran into was like local development. Originally, we kind of set forth and did Minikube. Minikube with node affinity is much different than a full-blown HA cluster that you would have inside a cloud or an on-prem environment. And so it's very important to know that these environmental changes can actually shape how your operator is going to be developed with and what is going to change over the course of time. Another thing that we ran into was installation. You want to make sure that when you have a consumable product, is as easy as possible to integrate with whatever technology stack that you have going forefront, right? But we also ran into trying two issues with this, that you try to macrotize so much of it, and then you end up actually painting yourself into a corner because you actually limit the flexibility and freedom that a consumer might want to do with your platform itself. In addition to this, if you kind of do this right off the bat, it kind of takes away from your core feature development. And so you'll start making assumptions that you wouldn't have done otherwise, and it can lead kind of down a rabbit hole. And Matt will kind of go into that a little bit more.
Yeah, so one thing we found is really important as people start to use your operator is to kind of make explicit the assumptions that you've built into it and kind of your perspective on building it. What we mean by this is that we built this operator with all the assumptions of how we kind of operate M3DB at Uber, which is we run these highly available clusters that are spread across multiple failure domains. And so we realized that we ended up baking in some of the assumptions about how we operate M3DB into our operator that might not be totally portable for everyone. We'll talk about that in a second. But one thing that we realized is that users are kind of at the different phases of what you might call like the Kubernetes maturity lifecycle, in the sense that you have some people that are still kind of like testing the waters. Maybe they're just installing your operator on a local Minikube instance just to see, like, does this thing even work? You might have some users who only have single master clusters in one failure domain because that's all they need to meet their requirements. And then on the other end, you have users that are running these highly available clusters spread across failure domains, or maybe they're using a more like polished distribution like OpenShift or something. And all of these use cases are valid, and you don't want to exclude any one user group from using your operator based on your assumptions. And to give you a concrete example of what we're talking about, so like I said, we run M3DB clusters that are spread across multiple failure domains. And for a while, and currently, though in development is changes to fix this, our operator actually requires that you have a Kubernetes cluster spread across 3 failure domains if you're using a M3DB, or if you're creating an M3DB cluster with a replication factor of 3. Because this is how we operate M3DB. But not everyone is really there yet, and you kind of have to meet your users halfway.
So let's talk about some of the successes, some of the results that we actually achieved from this, and what we accomplished. Yes, we got some clusters there. They're in 3 different zones. Currently, we have an operator running a subset of Uber's metrics right now for hosting services that are hosted inside our data centers. And one thing that we realized right off the bat, we were excited with this, But it presents a different paradigm. We were used to how we typically operated clusters. Now we had to shift over to how an operator is being used and how that would interface with our engineers itself. Let's talk about what it did really help out with, though. So let's go back to those 2 cycles. We have the reactive cycle, which changed dramatically now. So node becomes problematic. It signals to our operator something's going on. It'll triage based off of whatever cases that will catch, and tries to bring the cluster back into a healthy state. So there's no more paging of that operator engineer at 2 a.m. and have them wake up and kind of remediate the issue. So we went down to 0 minutes per day and 0 minutes per week, ideally. Let's talk about the other cycle where it's proactive. So previously, we would have those meetings about capacity planning and how we're going to manage our clusters, and it would take a lot of time off people's hands, especially when you had to enact those changes that we would set forth. With a stateful service like this, you have to reach certain goal states with your placement and addition or removal of nodes, and that was manually done. So an engineer would have to go in, do X amount of state changes to get a node in or out of the cluster properly and safely to make it reliable. And now the goal state is handled automatically, right? We've automated it within the operator now, and so it becomes almost as easy as just updating the manifest and let the operator roll through all those goal states, add the nodes, remove the nodes very safely in a reliable manner, and you don't have to deal with it. So ideally it would take it down to 20 minutes a week, but it's no longer this whole big parade of let's get everybody together, figure out things. It can be done within a config, or I should say a Git repo of some sort, just a config change that's there. So let's go over some advice for large stateful workloads, as I was mentioning, because this is a tough thing to do. Stateless apps are great, but stateful presents a lot more challenges to engineering. So first and foremost, we didn't just jump to Kubernetes. As Matt mentioned earlier, M3's been around for quite some time, the whole ecosystem that is, for years. And so we invested a lot of time and effort to make this platform reliable before it was even inside an automated operator such as Kubernetes. So first and foremost, make sure your tooling's there, make sure your platform's there, and nice and stable. Don't do a POC and say, you know what, we need to put this on Kubernetes. That's probably jumping the gun, I would say, a little bit fast. Second thing is, we only really approach this, as mentioned before, when we hit kind of scaling challenges. 40 plus clusters for an on-call engineer, it's kind of a lot to take on. It's burdensome. And so we only started looking at these automated solutions when operational complexity was at such a high scale that we needed to actually remediate this in a proper way. So we only started into this when scaling became an actual challenge for us. With that said, keep in mind, this is not a magic bullet. It's not going to solve all your problems. It's actually going to add more complexity to your platform. So be very mindful of adding yet another layer of operation on top of your cluster management, because there's yet another thing that you're going to have to think about while you're debugging or actually developing the actual automation that's there.
Other piece of advice if you're considering creating an operator for your own stateful workload is to kind of embrace this declarative approach to infrastructure management that Kubernetes has made so popular. We were already doing this in the sense that M3DB's cluster topologies are actually modeled as desired states that are stored in etcd that the M3DB instances themselves work to converge on and update when that convergence has occurred. So this actually meant that pretty much all our operator had to do was exchange this series of desired states between Kubernetes and M3DB and kind of take feedback from one, use it to inform decisions about the other, and it kind of just took part in this holistic reconciliation loop. If you compare this to something where, I don't know, if you have a database where if you're initiating a replace, you need to know that you initiated a replace and somehow keep track of that. in M3DB, with M3DB, all we have to do is look at etcd and look at our cluster topology and see kind of what the current state of the world is, because it's that one source of truth. Additionally, by storing our cluster topologies external to Kubernetes, we're able to avoid taking a hard dependency on the Kubernetes API to be able to operate our clusters. So this meant that even if the Kubernetes API is down or malfunctioning, so long as the pods themselves are still up, which Kubernetes makes great effort to ensure is the case under failure scenarios, that we could still actually make emergency changes to our cluster topologies by just modifying the state that's stored in etcd. So how are people starting to use this? This is probably the part that's been most exciting for us. So it's only been a few months that our operator's been out, and we already have people that are starting to use it and deploy it, are working on deploying it in production. So one thing that that's been really cool to see is we built M3DB as this long-term storage for Prometheus. It integrates really nicely. We act as a remote read-write endpoint, and additionally, our query service actually implements the PromQL query language. So you have like this native Prometheus integration with M3DB. And the Prometheus operator is a really popular way that people are running Prometheus in their Kubernetes clusters. And what's so cool is that with just a few lines of configuration change in your Prometheus clusters, you can integrate them with M3DB to use it as a long-term storage. And then additionally, we have users that have told us, oh yeah, I'm using the etcd operator to make my etcd clusters that M3DB talks to, and then I'm using the M3DB operator to make these M3DB clusters, and then I'm using the Prometheus operator to make these Prometheus clusters that are reading and writing from M3DB. And again, this theme that we've heard today, it's operators everywhere. And this has been really cool to see. Additionally, we're now on the OpenShift community-created operators page, and we're working on getting onto the operator hub. Looking at OpenShift has actually been really valuable for us because, again, talking about those assumptions that we built into our operator, we're running M3DB in these completely walled-off single-tenant environments, and we hadn't thought as much about things like locking down our pod privileges and the stricter default security policies that come with OpenShift have actually caused us to kind of go back and make sure that our clusters support the security configurations that more mature users might need.
So just to wrap up very quickly here, we have some future work that's there. More CRDs. Right now, we're pretty limited. We have it kind of coupled with our API query service that provides the read and write endpoints, as well as the actual storage node itself. We want to start separating this out and build a richer reliability story and scaling story for folks. Beyond that, we want even more CRDs. M3DB is only one part of M3. M3 is an entire ecosystem. We have a collection tier. We have a very reliable aggregation tier, ingestion tier. So we want to break this out a little bit more and provide people the entire ecosystem that we use inside Uber under an automated, operated fashion. Lastly, we would like to thank for our entire team that's not on stage right now, it's just the two of us, for helping to contribute to this project and make it actual realization and a possibility. For more information, there's some links on the slide here for the operator and general talks about M3 in general. Feel free to check it out. Thank you again from Matt and Paul.
Thank you.